My project is an AI-driven scaffold design optimization of 3D bioprinted skin grafts for improved burn wound healing. The aim of the project was to utilize an AI machine learning model to optimize different parameters within bioprinted skin grafts. And the goal is to reduce overall cost through efficient design creation and improve the healing rates for burn patients. Burns are an extremely common type of injury which destroys layers of skin. And for the most severe cases, standard treatment usually requires split thickness skin grafts. However, these grafts are limited by donor site morbidity, tissue availability, and scarring. So one solution that's been emerging is 3D bioprinting. And this is a promising form of burn treatment, which creates artificial skin constructs to mimic the native skin. Some challenges, however, in this bioprinting are the optimization of these parameters, such as porosity, structural integrity, and balancing all of these different parameters, which have like complex relationships that usually are non-linear. And in this study, it introduces AI for multivariable optimization of these parameters. And the study aims to maximize predicted healing rates for burn wounds. So for the methods, the computational environment development for the study was done within VS Code or Visual Studio Code using Python. And rather than use different applications like BioGears or CellSim, which are more complex and have like a lot like heavier and denser code, the study used Matplotlib's 3D toolkit within Python, digital twins of the scaffolds based on a synthetic dataset. And the dataset was generated using publicly available data from real-world wound data associated with leprosy patients. So the scaffold design and parameter mapping. To translate numerical outputs into an actual design, the study used a unit cell approach. This approach pretty much involves designing a very small microstructure and then repeating it until it fills a wound volume. And beneath here in table 1, you can see the mapping logic for these designs. And the script used a multivariate normal distribution and polynomial regression logic to model the interactions between the parameters. So that pretty much is just like covering the more complex relationships because they're nonlinear. And then generative architecture, 3D GAN or generative adversarial network architecture was selected because it's very computationally efficient for 3D voxel-based printing. And pixels for a 2D screen. A voxel is like a pixel for like a 3D structure, and it helps like models visualize what's being printed. And the framework generates complex structural variations of pore geometry and distribution, which are then evaluated by a regression ranker to predict the healing efficiency based on simulated surface area to volume ratios. And then literature-derived constraints. So the synthetic datasets were generated, I said before, it was generated from real-world wounds of leprosy patients. And this is the name here. Here's the model validation and fitness convergence. The regression ranker achieved an R-squared value of 0.59, indicating a moderate to strong predictive capability in correlating geometry with healing outcome. Additionally, by implementing genetic algorithms using the PyGAN library, a optimal fitness score was identified through evolutionary optimization. So pretty much the fitness is just talking about like the biocompatibility of these skin grafts. And what's happening here is the model is creating like 100 generations of these different models and ranking like how their fitness is improving. So comparing trial A to trial B, we can kind of see here how while trial A is like maximizing the healing potential with a peak fitness of 86.86, we can see how trial B is much more efficient in identifying that near optimal model because it's able to do it within the first 10 generations. And then here we have comparative analysis of optimized scaffold parameters. Trial A and trial B, they correspond to and as indicated here in trial A, the one that maximized healing outcome. We can see it used collagen-based biomaterial, and it focused on structural stability and larger pore sizes, and that's how it achieved the highest overall healing rate. And in contrast, trial B used chitosan with a higher porosity and smaller pore size. And then another important thing about this is despite the structural variations, the healing rate only differed by 0.7, and that's showing how the AI is successfully able to identify a stable optimal range for this recovery, even with the different parameters. Are some more results. This is simulation and structural interpretation. So here we can see this is in figure 2. It's a voxel-based 3D simulation for the scaffold architecture validates the logic using like the voxels, the cube shapes. We can see how there is like a high degree of like interconnected porosity, and that interconnectedness allows for the diffusion of nutrients throughout the system, leading to optimal healing. Additionally, the sponge-like structure creates a very high surface area to volume ratio, mimicking the natural architecture of the ECM or the extracellular matrix, allowing for cell migration and proliferation. So here in figure 3 is another model that was generated by the AI, and it depicts like the guidelines for this optimized model from trial A. It's just like a different way to visualize. By creating this like cross-sectioning structure, we create pillars. We create pillars that create mechanical strength for the model, forming a frame that can support the weight of a graft without filling the 250 microliter pores or micrometer pores. And in order to confine itself to the earlier defined limits over here, where you can see thickness 0.5 to 3, it wants to stay within the 0.8 millimeter thickness. So it constrained itself to 4 of 0.2 millimeter layers, which is like the average thickness for a filament for bioprinters. And this thickness allows for efficient metabolic exchange throughout the structure, ensuring high cell viability in the healing process. And then lastly, here is like a performance ranking of AI generated candidates. We can see here in table 4, this is like an AI generated table with a ranking system. And we can see how candidate 2 was overall selected with an efficiency score of 0.5060. And then down here in figure 4, this is the visualization of candidate 2 with the efficiency score of 0.5060. Instead of over here where it was like 9 by 9 or 10 by 10 around that, here it's like a 32 cubed voxel grid. And the reason for that is it allows the AI to more effectively calculate how permeable the structure is, as the higher amount of voxels and surface area for more pathways for the nutrients to pass through the graft. Here is a design comparison of AI optimized and traditional grafts, a bunch of different comparisons between like biomaterial, scaffold layout, thickness, porosity, healing time density, personalization, and cost. The main differences would be like the cost, personalization, healing time, and density. Implications of this AI optimization: researchers can shift away from trial and error to more efficient and predictive model-driven frameworks, which will reduce experimental burden. With further development, machine learning can combat current challenges and advance tissue engineering through repeated optimization. It will accelerate graft development, increase personalization, and help eliminate risk of incompatibility. And by implementing AI, biotech companies and research labs can create optimized models with increased speed and efficiency, which can in turn lead to huge savings for costs and materials. So limitations and future research for the study: there was a limited data set size and diversity, as there were only so many like patient examples, mostly from leprosy wounds. There was the use of relatively simple like regression-based methods. So this was used because there's like limited computational power, and more complex models like neural networks, gradient boosting, and Gaussian processes were not like feasible for the size. And then unaccounted for biological complexities. So the study didn't account for like all the different biological processes there are, such as like immune systems and patient-specific variability. So like accounting for age, weight, things like that. So for future work to contribute to bioprinting being used in clinical use, studies must address these limitations that constrain the study. So in conclusion, the study addressed current limitations of bioprinted skin grafts using machine learning to optimize parameters. With an R-squared value of 0.59, the model demonstrated moderate to strong predictive capability. The study used voxel-based methods to quantify structural features, such as porosity and surface area to volume ratio. Comparative analysis of generated scaffold candidates demonstrated the model's ability to select optimal parameter combinations. And by utilizing AI for multivariable scaffold optimization, bioprinting can achieve more efficient and rapid design generation, reducing development time and associated cost. The study illustrates the potential of AI use in improving structural integrity, functional performance, and the healing potential of these bioprinted skin constructs. However, the study was limited by dataset size and diversity, simplified models, and exclusion of complex biological processes. and future work must address these limitations in order to enhance the predictive capability of the model and clinical relevance of bioprinting as a whole.